Hi, these are the trigonometry lectures for educator.com, and we're here to learn about the inverse trigonometric functions. So we've already learned about sine, cosine, and tangent, and today we're going to learn about the inverse sine, inverse cosine, and inverse tangent, probably better known as arcsine, arccosine, and arctangent. So the arcsine function is also known as the inverse sine function. Basically, it's kind of the opposite of the sine function. So the idea is that you're given a value of x, and you want to find an angle whose sine is that value of x. So in order to make this work, sines only occur between -1 and 1. So you have to be given a value of x between -1 and 1. And then you're going to try to give an angle between -pi/2 and pi/2. So you try to give an angle between -pi/2 and pi/2 that has the given value as a sine. So if arcsine of x equals theta, what that really means is that the sine of that theta is equal to x. Now, there's some unfortunate notation in mathematics, which is that arcsine is sometimes written as sine to the -1 of x. This is very unfortunate because people talk about, for example, sine squared of x means sine of x quantity squared. And so you might think that sine to the -1 of x would be sine of x to the -1, which would be 1 over sine x. Now, that's not what it means. The sine inverse of x doesn't mean 1 over sine x. It means arcsine of x. And so this notation really is very ambiguous because this inverse sine notation could mean arcsine of x, or it could mean 1 over sine x. And so this notation is ambiguous because arcsine of x and 1 over x are not the same. The safest thing to do is to not use this notation, sine to the -1, at all. Let me just say, avoid this notation completely, because it is ambiguous. It could be interpreted to mean these two different things that are not equal to each other. So instead, it's probably safer to use the notation arcsine of x, which definitely means inverse sine of x and cannot be confused. The arccosine of x, the arccosine function, is sort of the opposite of the cosine function. So you're given a value of x, and you have to find an angle whose cosine is that value of x. And again, the angle of x, the value of x you must be given, would have to be between -1 and 1, because those are the only values that come up as answers from cosine. And then what you try to do is produce an angle between 0 and pi. So there's 0, pi/2, pi. You try to produce an angle between 0 and pi that has that value as its cosine. And just like we had with sine, there's the problem of this misleading notation, cosine to the -1 of x. It could be interpreted as 1 over cosine x, or it could be interpreted as arccosine of x. And so the best thing to do is to avoid using this notation completely. Cosine to the -1 of x is just misleading. It could be interpreted either way. Try not to use it at all. Instead, stick to the notation arccosine x. Finally, arctangent is known as the inverse tangent function. You're given a value of x, and you want to find an angle whose tangent is x. And for arctangent, we're going to try to find angles between -pi/2 and pi/2, because that covers all possible tangents we could get. If arctangent of x equals theta, that really means that tangent of theta is equal to x. Just like with sine and cosine, we have this potentially misleading notation. Tangent inverse of x could be interpreted to mean arctangent of x or 1 over tangent of x. Those are both reasonable interpretations, but they mean two different things. So again, let's try to avoid this notation completely. Avoid this notation completely because it could mean two completely different things. So we'll just try not to use that at all. When we're talking about inverse tangent, we'll say arctangent instead of tan negative 1. So let's get started with some examples. First off, we have to identify the domain and range of the arcsine function and then graph the function. Well, let's start out with a graph of sine x, because arcsine is really meant to be an inverse to sine x. So I'll start with a graph of sine x here. Now, remember that when you're trying to find inverse functions, you take the function and you reflect it across the line y equals x. But in order for something to be a function, it has to pass the vertical line test. If you draw a vertical line, you shouldn't cross the graph twice. But since we're reflecting across the line y equals x, that kind of switches the x's and y's. So we want something that will pass the horizontal line test. Let me draw this in red. We don't want to be able to draw a horizontal line and cross the graph twice. And as you see, when I've drawn these horizontal lines, we cross the graph in lots of places. So we have a problem when we want to define the inverse sine function. The way we solve that is by not using all of the sine graph. We just cut off a piece of the sine graph that will pass the horizontal line test. And so I'm going to cut off a piece of the sine graph from negative pi over 2 to pi over 2. And if you just look at this portion of the sine graph, you see that it passes the horizontal line test. And that means we can take the inverse just of that part of the sine function. So let me draw what that looks like when we reflect it. So we're just taking this thick piece here, and I'm going to reflect that across that line y equals x. And now the notations that I had on the y and x axes are going to switch. So it goes from now negative 1 to 1 on the x-axis and negative pi over 2 to pi over 2 on the y-axis. And I can't keep going with this. I can't draw the rest of the graph because if I do draw any more, I'm going to get something that fails the vertical line test. It won't be a function anymore. So this is the entire arcsine function. So the domain here, it's all the numbers you can plug into arcsine. That's all values of x with negative 1 less than or equal to x less than or equal to positive 1. We can't plug any other values of x into arcsine, and that's really because in the other direction, the only values that come out of the sine function are between negative 1 and 1. So the only values that you can plug into the arcsine function are between negative 1 and 1. The range, the numbers that come out of the arcsine, all values of x between negative pi over 2 and pi over 2. let me write that as y, because we think of those as the values coming out of the arcsine function. So those are all the y values you see here, and you see that the smallest y value is negative pi over 2, and the biggest y value we see is pi over 2. So arcsine takes in a number between negative 1 and 1, gives you a number between negative pi over 2 and pi over 2, and its graph looks like a sort of chopped off piece of the sine graph. Remember, the reason we had to chop it off is to get a piece of the sine graph that would satisfy the horizontal line test so that the arcsine graph satisfies the vertical line test and really is a function. So in our second example here, we have to find the arcsine of the sine of 2 pi over 3, and then some similar values for arc cosine and arc tangent. So the first thing to do here is really to figure out where we are on the unit circle. There's 0, pi over 2, pi, 3 pi over 2, and 2 pi. So let's figure out where each of these angles is on the unit circle. 2 pi over 3 is over here. There's 2 pi over 3. And remember, arcsine is always between negative pi over 2 and pi over 2. Arcsine is between negative pi over 2 and pi over 2. So there's negative pi over 2 down here. We want to find an angle between negative pi over 2 and pi over 2. So on the right-hand side, that has the same sign as 2 pi over 3. Well, sine is the y value. So we want something that has the same y value as 2 pi over 3. So that angle right there has the same y coordinate as 2 pi over 3. That's pi over 3. So from the graph, we see that pi over 3 has the same sign as sine of 2 pi over 3. So arcsine of sine of 2 pi over 3 is pi over 3. It's an angle whose sine is the sine of 2 pi over 3. Let's try the next one. Negative 5 pi over 6. Well, negative pi is over there, so 5 pi over 6 in the negative direction puts you over there. There's negative 5 pi over 6. Negative 5 pi over 6. We want an angle whose cosine is the same as the cosine of negative 5 pi over 6. Cosine is the x value, so we want an angle that has the same x value as the one we just found. And there it is right there, 5 pi over 6. And that's between 0 and pi, which is the range for the arc cosine function. It's always between 0 and pi. So that means that arc cosine of the cosine of negative 5 pi over 6 is 5 pi over 6. That's an angle between 0 and pi that has the right cosine. Finally, we want to find the arctangent of 3 pi over 4. 3 pi over 4 is over there. So there's 3 pi over 4. We want to find an angle that has the same tangent as that one. And remember, arctangent is forced to be between pi over 2 and negative pi over 2. So we want to find an angle between negative pi over 2 and negative pi over 2 that has the same tangent as 3 pi over 4. Well, if we go straight across the origin there, we started with an angle whose cosine is negative and sine is positive. This angle right here has a positive cosine and negative sine. So it'll end up having the same tangent, and that angle is negative pi over 4. That's an angle inside the range we want that has the same tangent. So arctangent of tangent of 3 pi over 4 is negative pi over 4. So those are really quite tricky. What we're being asked to do here in each case is we're given an angle, for example 2 pi over 3. We want to find arcsine of sine of 2 pi over 3. So we look at the sine of 2 pi over 3, and then we want to find another angle that has that sine, but it has to be in the specified range for arcsine. So we're really trying to find what's an angle between negative pi over 2 and pi over 2 whose sine is the same as sine of 2 pi over 3. And that's why we did this traversal to find the angle pi over 3 that has the same sine as the sine of 2 pi over 3. And so that was kind of the same process in all three of them, finding angles that have the same cosine as negative 5 pi over 6, but is in the specified range, finding an angle that has the same tangent as 3 pi over 4, but is in the specified range. In our third example here, we're asked to identify the domain and range of the arctangent function and graph the function. Well, remember when we graphed arcsine, we started out with a graph of sine. So let me start out here with a graph of tangent. I'll graph it in blue. Has asymptotes at pi over 2. And then it starts repeating itself. It has period pi. So this is 0, pi over 2, negative pi over 2, and that's pi, 3 pi over 2. So what I graphed in blue there is tan theta. Now, I want to take this graph and I want to flip it around the line y equals x. Let me graph the line y equals x. There's y equals x. But I want to get something that it will be a function. So it has to pass the vertical line test after I flip it. That means it has to pass the horizontal line test before I flip it. And just like with sine, the tangent function fails the horizontal line test badly. You can draw horizontal lines and intersect it in lots of places. So just like with sine, we're going to cut off part of the tangent function and use that to form the arctangent function. So we're going to cut off just one of these curves. So I'll cut it off these asymptotes at negative pi over 2 and pi over 2. And I'll just take this part of the tangent function and I'll flip it around to make the arctangent function. So I'll do this in red. Arctangent of x. So I'm going to flip around just that one main branch of the tangent function. And so since the tangent function had vertical asymptotes, the arctangent function is going to have horizontal asymptotes at negative pi over 2 and pi over 2. So those are my asymptotes right there at negative pi over 2 and pi over 2. We're also asked to identify the domain and range. So the domain means what numbers can we plug into arctangent of x. Domain is all values of x, because we can plug any number in on the x-axis here and we'll get an arctangent value. So negative infinity, less than x, less than infinity. The range is all x with, okay, let me write this as y because these are values on the y-axis. All y with negative pi over 2 less than y less than pi over 2. And let me emphasize here that pi over 2 and negative pi over 2 are not included. Pi over 2 themselves are not in the range. So these inequalities, they're not less than or equal to, they're strictly less than. And the reason for that is that the arctangent function never quite gets to negative pi over 2 or pi over 2. It goes down close to negative pi over 2, and it goes up close to pi over 2, but it never quite gets there. And the reason for that, if you kind of look back at the tangent function, was that these asymptotes never quite get to negative pi over 2 or pi over 2. You can't take the tangent of negative pi over 2 or pi over 2 because you're trying to divide by 0 back with the tangent function. So to understand this problem, really you have to remember what the graph of tangent theta looks like. Then you take its one main branch and you flip it over and you get the graph of arctangent of x, and the domain and range just come back to anything's in the domain. The range can go from pi over 2 to negative pi over 2, but you don't include those endpoints. And the asymptotes are at the horizontal lines at negative pi over 2 and pi over 2.